In this video, we're going to see that conditionally convergent series are naughty. They're very, very naughty indeed. So, what do I mean by naughty? Well, when we have an infinite sum series, we would like that to have the same properties as my normal, regular, ordinary sums. And one of the properties that we really like about sums is that we have commutativity. 1 plus 2 is equal to 3, and 2 plus 1 is also equal to 3. Well, when we have conditionally convergent series, we lose completely the commutativity property, and when we change the order in which we add things, very weird things could happen. So let's start with one example. We're going to look at our very old friend, the alternating harmonic series. This, remember, is 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5 minus 1 over 6 plus 1 over 7 and so on. And right now, I want you to trust me. I cannot prove it to you now, but we can do it in the future if you like. And it's that this adds up to the logarithm of 2. I know, mind-blowing, but it is true. So this sum is equal to natural logarithm of 2. And I'm going to show you that if I change the order in which I add these terms, I will get a completely different sum. So let's see. We're going to reorder the terms in the following way. We're going to take the positive terms in blocks of 1 and then followed by negative terms in blocks of 2. So 1 positive, 2 negative, 1 positive, 2 negative, 1 positive, 2 negative, and see what happens. So here I'm rewriting it, and if you see here we have these green ones are the positive, the pink ones are the negative, so it's easy for you to track it. We have positive, 2 negative, 1 positive, 2 negative, 1 positive, 2 negative, and so on. And now I'm going to group them in a way that it's easier for me to add things up. So I'm going to group in this way. And if you see here, 1 minus 1 half is 1 half. So we have 1 half minus 1 over 4. 1 over 3 minus 1 over 6 is what? It's 1 over 6. So we're going to continue doing these groupings, and what you're going to see is that we end up with this. We have 1 over 2 minus 1 over 4 plus 1 over 6 minus 1 over 8 plus 1 over 10 minus 1 over 12 and so on. Oh, but look at this. What happens if I take common factor 1 half? Well, this is 1 half times 1 minus 1 over 2 plus 1 over 3 plus 1 over 5 minus 1 over 6 and so on. Oh, we have 1 half times the alternating harmonic series. Okay, so that means that the sum should be 1 half times the natural logarithm of 2. Oh, but wait a minute. We said that this sum was equal to the logarithm of 2. Ooh, that's insane. That's absolutely mind-blowing. We have that the same series adds to both logarithm of 2 and 1 half logarithm of 2. Okay, that's not very nice. Why is this happening? What's the problem with this? Well, let's see. In general, when I swap the order, which is what I did here, you see I took now 1 positive, 2 negative, 1 positive, 2 negative. In general, we call a reordering of a series is another series that contains exactly the same terms, but in a different order, right? That's what we did. And we're going to see that when we have a conditionally convergent series, then we can reorder it to obtain any result we want. So we can make it to be convergent to any real number we want. We can make it divergent to positive infinity, and we can make it divergent to negative infinity. So whenever someone gives you a conditionally convergent series, you can take it, start shuffling around the terms in such a way that you can make it converge to your favorite number. Any number you like in the world, you can make it converge to that one. You can make it diverge to positive infinity, and you can make it diverge to negative infinity. Okay, this sounds insane. How can we do that? Well, we're going to reorder the alternating harmonic series again, so the sum is equal to 2. And this is how I'm going to do it. You see, I'm going to first add positive terms until that sum is above 2. Just the moment I hit 2, I stop adding positive terms. So in this case, I have to add 1 plus 1 over 3 plus 1 over 5, up to 1 over 15. If you do 1 over up to 1 over 13, that's still less than 2, so you really need to get to the adding the 1 over 15 to get this number here, 2.0218, blah, 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 blah. Okay, now we're going to add negative terms until the partial sum is just below 2. So the moment you hit a value that is less than 2, you stop. Actually, if we do this minus 1/2, we get 1.52 something, so we're already below 2, so we don't need to do anything else. And now we're going to repeat the process. To the thing I have now, I'm going to add positive terms, the positive terms that I haven't used yet, until I go again above 2. So here I have to add all the terms, positive terms 1 over 17, 1 over 19, plus da da da, up to 1 over 41, and I went just above 2. And now I'm going to subtract negative terms, right? Take away something until I'm below 2. And again, I just had to do minus 1/4, and that was enough to bring me below 2. I'm going to repeat the process again. I'm going to add as many positive terms I need. So when I do that, I go back again above 2. And I needed to add 1 over 43, 1 over 45, up to 1 over 69. So we did all those positive terms, and we went above 2. And now I'm going to again add negative terms until we go below 2. And well, I will continue doing this process forever. Remember, I have infinitely many terms, so I can continue doing this forever. Oh, that's very interesting. So here in this picture, I have the outcome of the partial sums in each step. So here, for example, in the first one, it's when I added the first 8 terms and I ended up with 2.02. Then I did minus 1/2, so I ended up with 1.5 something, right? So it's there. Then I added a bunch of other terms, and it brought us to adding something like 22 terms. And we are very close to 2. Then we had to subtract 1/4, brought this back down. Then we added a bunch of positive terms, and after adding all the ones that we needed to go above 2, then we subtracted 1 over 6, and we continue doing this process. So here you can see these dots are not all the partial sums. It just indicates the value of the partial sums at the points where I stop my step. So this is the outcome of step 1, step 2, step 3, step 4, 5, 6, 7 from this process. So here we see that those values are getting closer and closer and closer to 2. So my expectation is that if I repeat this process forever, indeed I'm going to be able to be as close to 2 as I would like to be. And this is brilliant. And there was nothing really special about 2. I could repeat the same process with pi, right? Go just above pi, then subtract to go below pi, then add to be above pi, and so on. So I can do this process with anything. But then, what was important about this series that allows me to do this? Well, there are 3 very important features of this alternating harmonic series that allows us to do this. First one, if you look at the sum of just the positive terms, this one, they diverge to positive infinity. Because you see, 1 over 2n minus 1 is bigger than 1 over 2n. And we know that the series of 1 over 2n is just 1/2 of the harmonic series, so it's infinity. It diverges to infinity. And the same thing we can do with the negative terms. If we add all the negative terms, that diverges to negative infinity. Using the same argument, right? Like the sum of negative 1 over 2n, that you can look at as negative 1/2 times the sum of the harmonic series, which is diverges to infinity, so you can think of negative infinity. And then we have another property, and is that the terms, like 1 over n, goes to 0 as n goes to infinity. And these are the key features of the alternating harmonic series that allowed us to actually do this process, to sum to any value. So the way we do this is that if we want to sum to a number s, any number s, what we need to do is we add positive terms until the sum of the partial sums get above s. And this is possible because the series of the positive terms diverges to positive infinity. So I know that if I add enough terms in this series, I can be larger than any number that I like. And then, well, given that result that I got that is just above S, I want to now add negative terms until now my sum goes below S. And remember, I can do this because I know that the sum of the negative terms goes to negative infinity. That means that I can make, given that I use enough terms, right, I can make it as negative as I need it to be. And that will compensate, right? If I went above S, now I need to find a negative number that will allow me to go below S. So that's the process. And then, well, we repeat. We will go back to step 1 and we continue doing this process. Okay, so we have a way of going above S and below S. But then how can I guarantee that I'm getting close, very, very close to S? Well, you see, because the limit of the 1 over n is equal to 0, each time that the partial sum goes above 0 or below 0, they stay closer to S, because the distances that I'm traveling become much, much smaller. And that is the idea of this proof, and that is how this works. So, okay, this worked for the alternating harmonic series, but how can I make it work for any conditionally convergent series? Well, how can we do this? Well, in general, if we know that a series is conditionally convergent, the series of the positive terms is going to diverge to infinity. Or we can look at it as the series of these an plus that we defined previously, that is infinity, and the series of the negative terms diverges to negative infinity. So we do the negative of the an minus, that is going to negative infinity, and the limit as n approaches infinity of the absolute value of the terms of my sequence is equal to 0. If I have these three properties, then I can do the exact same reasoning that we did before to show the same result now for any conditionally convergent series. So then your task would be, well, proving that this is true. 3 is actually the easiest one. Probably you already even see how you can do it. 1 and 2 are a bit harder, but once we do 1, 2 would be the same thing. So we're going to have as an exercise to show that if I know that a series is conditionally convergent, then the sum of the an plus, the sum of the positive term, and the sum of the an minus, of the negative parts, are both divergent. And here is a hint. You want to do this in steps. We want to show that if I know that the sum of the absolute values is divergent, then either the sum of the an plus, so the sum of the positive parts, or the sum of the negative parts divergent, or both are divergent. And then you're going to show that if I know that my series converges, and I know that, for example, the sum of the positive term is divergent, then the sum of the negative term has to be divergent. So then, once you do that, you will be able to put all the pieces together to see exactly what you need to do.